Hello everybody, welcome to my second lecture. This is going to be a whistle-stop tour through the development of quantum mechanics, talking through some key principles and concepts as we go along. Some of these topics you may have heard about before, but some of them will be completely new to you, so don't worry if you don't grasp them straight away. Quantum mechanics is notorious for being difficult to comprehend first time round. I would also like to say that there are some amazing resources on the internet if you'd like any alternative explanations about anything, or you just want to dig deeper into certain topics. So, without further ado, this is Quantum Mechanics, from igniting the sun to imaging atoms. To start off with, I just want to talk a bit about what quantum mechanics actually is. Many people may have heard about this theory, but don't actually know what it is. Quantum mechanics is a fundamental theory in physics that describes the physical properties of matter and energy at the atomic and the subatomic scale. To date, quantum theory is our most accurate and successful theory produced by physics. We know that classical physics works with continuous quantities, such as energy and momentum. However, quantum physics discretizes these values. What does this mean? Well, in quantum physics, these continuous values are now discrete. For an example, in quantum theory, energy is a discrete value. It comes in steps, indivisible quantities known as quanta. An example of a quanta of energy is a photon, as we'll see later. Another key topic in quantum mechanics is wave functions. Now, we will go over these later, so don't worry if you haven't heard about them before. So, let's start with some history about light. Throughout history, there have been many attempts to interpret what light actually is. These range from light being a particle, to light being a wave, and even to light being rays that come out of our eyes, and that's how we see everything. Around 1670, Robert Hooke and Christian Huygens developed a mathematical framework for light being a wave. They were able to describe the refraction of light very well. This wave picture was very successful at reproducing light's other behaviors, and it even described the results of Young's double-slit experiment. Now, you may have heard about Young's double-slit experiment before. If not, you'll definitely hear about it in year 13. The basics of this experiment are shown on the slide. A monochromatic source of light is passed through a single slit, and it impinges on a second barrier which has two slits in it. What do we expect to see on the other side? Well, if light is a wave, we should see an interference pattern. As shown on the diagram on the left, when a wave propagates through these two slits, they'll interfere with each other at certain points. When the peaks and the troughs coincide, there'll be constructive interference and we'll get a higher intensity. And when they do not coincide, we'll get a lower intensity, i.e. destructive interference. So, what do we see on the other side? Well, what we observe is exactly this. We find an interference pattern on the recorder screen. This shows that light has wave-like properties. This was groundbreaking at the time due to light being a historical struggle. So what happened next? Fast forward to the late 1890s, and this fella, Max Planck, was working with light bulbs, trying to make them more efficient at producing visible light. In doing so, he birthed quantum theory. So this is a fun fact that we wouldn't have quantum theory without light bulbs. At this time, classical wave theory was still accepted. So, Planck, using classical wave theory, wanted to predict the intensity of light radiated from a body at temperature T. Well, the classical results were giving nonsense at the time. They predicted that there was an unbound amount of energy in the UV range of the spectrum. What was going on? Well, as we can see, the equation for the intensity from classical theory says that the intensity is proportional to 1 over lambda to the fourth, which means that in the UV part of the spectrum, This blew up to infinity. Planck was very annoyed by this problem and decided to throw classical physics out the window. Planck worked backwards from his observations to determine the correct form of this intensity distribution, and he did this by making some strange and very bold assumptions. A fun fact that when commenting on some of these assumptions that he made, he described them as an act of despair. I'm sure everyone has felt like this during their studies, and if not, you definitely will when you get to university. Planck assumed that the interaction between the atoms and the light was itself quantized. This means that the energy exchange was in little packets of energy, with E equals h nu equal to hc over lambda, where h is Planck's constant, nu is the frequency of light, c is the speed of light, and lambda is the wavelength. Note that this is very different from quantizing the actual electromagnetic waves themselves. He quantized the interaction. In doing so, he solved the UV catastrophe. He obtained that the intensity of light was given by this expression here, which included his Planck's constant. This was the absolute birth of quantum physics. So what happened next? Of course, it was Einstein. In 1905, and yes, for those of you who've seen my previous lecture, this is the same time that he was developing his theory of special relativity. He extended the ideas of Planck to quantize light itself. So what does this mean? Well, in Einstein's theory, light itself is made up of quanta, these individual, indivisible packets of energy that are absorbed or emitted as quanta, known as photons. So why did he do this? Well, he wanted to explain the photoelectric effect. You may have come across this effect before, and again, if not, you'll definitely study this effect in year 13. What was found that the energy of electrons that are emitted from a metal plate increased only when the frequency of the light increased, and not the intensity. So this means that a low intensity, low frequency beam of light produced a small amount of low energy electrons being emitted, whereas a high intensity and low frequency incident light would produce a larger amount of low energy electrons being emitted. This is at odds with the classical wave theory of the time. So let's see what wave theory predicts versus what the experiment found. Well, the first thing that wave theory predicts is that the intensity of an electromagnetic wave depends on its amplitude and not its frequency. Therefore, the photoelectric effect should occur at any frequency. The magnitude of the photocurrent should not be dependent on the frequency, just the amplitude. The second thing that classical wave theory predicts uses the concept of a work function. Now, the work function of a material is just the minimum energy required to eject a single electron. If the light falling on the surface was very faint, it would take a finite amount of time in order to absorb the total energy needed. Therefore, we should get a photocurrent at any frequency. But what did the experiment find? Well, the first experimental finding that contradicts the wave theory was that the photocurrent did depend on the frequency of the light. Light with a frequency less than a certain threshold frequency did not produce a photocurrent. The second thing the experiment found was that there was no measurable time delay when light was turned on and when the photoelectrons were emitted from the surface when the frequency was above this threshold frequency. So, Einstein extended Planck's theory to assume that light itself was made up of photons. This means that he assumed that light behaved as a particle, these particles being photons. These are absorbed fully or not absorbed at all. Photons are quanta of the electromagnetic field, and with this he explained the experimental results of the photoelectric effect. Einstein actually won the Nobel Prize for the photoelectric effect. And another fun fact, Max Planck, the father of quantum mechanics, didn't think that it would stay around for long. He thought that it would just be upgraded by another classical field theory. Einstein did not think this. So, what's the explanation with photons? Well, individual photons are absorbed by individual electrons, either fully or not at all. This contrasts with the continuous energy transmission in wave theory. This also means that the electrons can only escape if it obtains a correct energy, E greater than hf. Photons also explain the findings of the photocurrent only being seen at a certain frequency. If the photons did not have the energy required to excite the electrons out of the material, then the electrons wouldn't, because they wouldn't absorb the photons. This is consistent with a higher intensity resulting in a higher photocurrent and not a higher energy. This also explains why there is no time delay between the absorption and the emission of these electrons. So, light's a particle? Well, not exactly. If you're thinking of a localized ball, this will get you into a lot of trouble. You should note that quantum mechanics is a probabilistic theory, meaning that these photons are delocalized. There are probabilities of finding them at certain places. We'll come back to this when we discuss electrons. So, what is going on? Light is both a wave and a particle? Well, this is best summed up by Einstein himself. He quoted, "It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explain the phenomena of light, but together they do. And this is a core concept of quantum mechanics and is something to really get your head around." Chronologically in our story, the next step is the first model of the hydrogen atom that used quantum mechanics. This was produced by Niels Bohr, and this is a model you may be very familiar with. You probably have come across this in chemistry, but not by this name. Niels Bohr produced this model using the work from Einstein and Planck. Bohr's postulates were based on both classical physics and quantum physics that was available to date. He wanted to explain hydrogen spectral emission lines and the Rydberg formula. When we excite hydrogen, we find that it only emits certain frequencies of light. These frequencies can be thought of as a characteristic fingerprint, and every element has a separate characteristic fingerprint. This concept is used in spectroscopy all the time, and this is a very big pillar in astronomy and astrophysics. He thought about the photon emission changing the internal energy of the atom. Each atom only exists for certain internal energy values. This means that each atom has a set of possible energy levels given by n equals 1, n equals 2, n equals 3, all the way up to n equals infinity, where the electron is free from the atom. The difference in energy between two of these energy levels would be the photon that was emitted when an electron moves down from one energy level to another. Similarly, if you were to shine light onto this atom, it would only absorb the energy at a certain frequency corresponding to this difference in energy between the energy levels. Niels Bohr quantized the energy levels within atoms. An atom can have an energy equal to the energy level only, and there is no intermediate levels. Therefore, if you had light that was not enough to promote an electron from one level to another, it would not be absorbed. Atoms of the same element have the same set of levels, and atoms of different elements have a different set of energy levels. When he derived the energy of the nth energy level, he found the formula E equals minus 13.6 electron volts over n squared times by z squared, where z is the atomic number and n is the principal quantum number. Minus 13.6 electron volts is known as the Rydberg energy. He calculated this for the expected frequencies as seen for hydrogen, and they matched the experimental data remarkably well. Should note that this model is limited to hydrogen, and it fails to explain the more complex spectra of atoms which have multiple electrons. But this was a huge development in the history of quantum theory. So, what's next? Well, in 1924, Louis de Broglie, for his PhD thesis, postulated that it's not just light that has this wave-particle nature. He thought, if light can behave as a wave and a particle, can particles also behave like waves? Well, specifically, he developed his theory using the wave nature of electrons, and generalizing the formula from Einstein, E equals hf, where h is Planck's constant and f is the frequency, he found that the momentum of a particle is equal to Planck's constant over its wavelength. Shortly after, it was proven that particles also had wave nature, and this was done via electrons using what's called electron diffraction. And it was in an experiment called the double slit experiment. Let's watch a short video on this.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
But if particles have wave nature, why don't we see it? Well, this comes down to the absolutely tiny magnitude of Planck's constant. Massive objects have a large momentum when we compare it to h. And using de Broglie's wavelength formula, this means that they have very, very tiny wavelengths. Therefore, the effects are so small that they are literally never noticed on the scale that we live every day. You may have heard in that clip the term wave function, or you may have heard about these before. These are paramount in quantum physics and are how we describe quantum states. So, wave functions are mathematical descriptions of quantum states, and in general they are complex functions. If you haven't studied complex numbers before, don't worry, in a later live event I'm going to be going through complex numbers. So we no longer describe particles as localized, but we describe them in terms of waves, and we do this via wave functions. To obtain observables about a quantum system, for example, the position or the momentum of the particle, we do this by operating on our wave function. This is done through mathematical expressions and by squaring the wave function. We interpret this wave function as a sort of probability density. An example is best seen by considering the position of a particle. You should note that wave functions contain all possible information about a system, and also that quantum mechanics is an entirely probabilistic theory. So, shown on the right-hand side are three different wave functions. By squaring the absolute value of these wave functions, it gives the probability density of the wave function. This is a measure of how probable it is to find, let's say, an electron at a certain place. And you should know that there are infinitely many wave functions. So, for the first wave function, we see that we are most likely to find the electron at x equals 0. For the second wave function, we are equally likely to find the electron in two different positions. And for the third, we are much more likely to observe the electron to be on the right-hand side. So, let's talk a bit about wave functions and superposition. You may have come across the concept of constructive and destructive interference during your study at A-level. This principle of superposition uses this constructive and destructive interference. The principle of superposition states that a quantum system can exist in multiple states simultaneously. When we observe quantities about the system, our wave function collapses into one of these states, so we get a definite measurement. Until we make this measurement, the system exists in all possible states at once. So let's take an example of the pound coin. If we are to observe the pound coin, we have two different quantities that it can be, heads or tails. Therefore, we can construct a wave function for the coin in quantum theory, where we have one wave function that resembles our heads and one wave function resembling our tails, multiplied by a prefactor. And this prefactor is proportional to the probability of getting that outcome. Therefore, if we were to take the magnitude squared of this coin, of this wave function of the coin, we would find the probability of getting heads or the probability of getting tails. When we observe the system, this wave function that's made out of different wave functions, i.e. it's a superposition of wave functions, collapses down into one of them and we get a definite measurement of heads or tails. We can extend this to an electron. An electron can be in many possible states at once, given by the superposition of psi1, psi2, psi3, and we go on, all with different probabilities. However, when we measure a quantity of this electron, this wave function collapses into one of these states, so we can get a definite measurement. This is popularized in Schrödinger's cat. Now, what is this? Well, I'm sure you've heard of this before. We have a cat in a box with a poison vial that can break. Now, until we open the box, we cannot say for definite whether the cat is alive or dead. Therefore, the cat is in a superposition between being alive and being dead, and it's only when we observe the cat does this wave function collapse and we get a definite measurement. Next up on our journey is the Heisenberg uncertainty principle. Many of you may be familiar with this name. He's most famous for his uncertainty principle, which is a pillar in quantum mechanics, but he did a lot more for quantum mechanics than just this. Heisenberg was concerned with the limitations of simultaneously measuring certain pairs of physical properties. For an example, measuring position and momentum simultaneously. What he found challenged the classical notion that simultaneous measurements of quantities were allowed, with definite certainty. Heisenberg's uncertainty principle implies that the more precisely you try to measure one of these quantities, the less precisely you will be able to know the other. This is because the act of measuring one of these quantities disturbs the other property, introducing some inherent uncertainty into the system. Werner Heisenberg was a huge contributor to quantum theory, and he basically built it from the ground up in matrix form. Heisenberg's uncertainty principle gives us an absolute limit on how precise measurements can actually be when taken simultaneously. The most commonly seen form of Heisenberg's uncertainty principle is given by the equation on the bottom. This states that the uncertainty in position times by the uncertainty in the momentum must be greater than or equal to Planck's constant over 4 pi. A fun fact about Werner Heisenberg was he was a very patriotic guy to Germany, and he was one of the head scientists for the Nazis, researching if an atomic bomb was possible. He actually made significant ground before his lab burnt down. Some people today believe he did this due to mistreatment from the Nazis, and it wasn't just an accident. Let's take a quick look at an example of how to use Heisenberg's uncertainty principle. So, in an experiment determining the position and the momentum of a marble on a table, a scientist records simultaneously that the error on the marble's position is given by 0.17 times 10 to the minus 9 meters, and the uncertainty in the momentum is given by 2.6 times 10 to the minus 25 kilograms meters per second. Do you believe this? I encourage you to pause the video and see if you can solve this. Well, Heisenberg told us that simultaneous measurements have an inherent error given by delta x, delta px, greater than or equal to h over 4 pi. Using the scientist's measurements, we obtain that 4.42 times 10 to the minus 35 is greater than or equal to 5.27 times 10 to the minus 35. Therefore, the scientist's results are definitely not trustworthy, as this breaks a fundamental theory in quantum mechanics. Now let's go through one of the very cool consequences of quantum mechanics: quantum tunneling. When an electron encounters a barrier with an energy that's lower than the barrier, we know that in classical mechanics, this electron cannot be found on the other side of the barrier. So let's use our knowledge of quantum mechanics so far to analyze the situation in the case of quantum. We know that particles behave like waves, so we can describe this electron as a wave in a wave function. We also know that there is a fundamental limit to the precision of measuring momentum and position of the electron simultaneously. When the electron encounters this barrier, the position and the momentum become uncertain. The wave function of the electron therefore has a non-zero value on the other side of the barrier. It is much less probable to find the electron on this side of the barrier, therefore the amplitude of the wave function that side is lower. The wave function therefore exponentially decays inside the barrier, and we get a probability for finding the electron on the right-hand side. This is how quantum tunneling works. The concept of quantum tunneling is not only used in a lot of our technology today and is how we store a lot of our data, but it also has some incredible consequences for the sun, as we'll see later. So let's just go through a summary so far. As we've seen, in the 1900s, Max Planck decided to quantize the interaction between light and matter. Very soon after, in 1905, Einstein developed this theory further to postulate that light is actually a particle, photons. These are quanta of the electromagnetic field. In 1913, Bohr then produced the first model of the hydrogen atom that used quantum theory. It then took a while until the wave-particle duality of matter was postulated via Louis de Broglie in 1924, giving us electron diffraction. Very soon after this, in 1927, Heisenberg produced his uncertainty principle. It's important to note that from 1900 to 1927, our picture of the universe completely changed. Up until this point, classical mechanics was accepted. The universe was deterministic. Within 27 years, we found that the universe is actually probabilistic. So what's something in quantum mechanics we haven't yet touched upon? Well, we all know of Schrödinger's wave equation. This is arguably one of the most famous equations in physics. we've seen that particles can be described by wave functions. The way that wave functions evolve in time and space is given by the Schrödinger equation. Erwin Schrödinger was another father of quantum theory. Now, this equation is very important and it's used all throughout quantum physics. I would suggest noting it down because we will use it in a later live event to solve some quantum mechanical systems. So, what about relativity and quantum mechanics? Don't these two not go together? Well, there have been many attempts to marry the theory of special relativity and quantum mechanics after the development of the Schrödinger equation. The first of this was done by Klein-Gordon, but the equation yielded negative energy results and only worked for spinless particles. This chap here, Paul Dirac, reformulated the theory to produce a quantum theory that was consistent with special relativity. However, his equation, the Dirac equation, still had negative energy solutions. What was going on? Well, it turns out Paul Dirac had accidentally stumbled upon antiparticles. What are these negative energy solutions? What are these antiparticles? Well, as you can see, the solutions to the Schrödinger equation for these negative and positive energy solutions are quite complicated. But Dirac had an interpretation for these negative energy solutions. He modelled the vacuum as an infinite sea of particles which have negative energy. If we have enough energy to excite these negative energy particles into positive energy solutions, we create antiparticles. This is because in the Dirac sea interpretation, the absence of a negative energy particle is equivalent to behaving like a positive energy antiparticle. Richard Feynman also came up with another interpretation of these negative energy solutions. He found that if he reversed time in the equations for the negative energy solutions, they just became positive energy solutions. This leads him to say that antiparticles are just particles that move backwards in time. This can be seen in all Feynman diagrams, as shown in an example on the right hand side. We use these all the time in particle physics, and as you see, the antiparticle of the electron, the positron, is travelling backwards through time. We'll see a lot more of these in the upcoming lecture on particle physics, but these are some of the interpretations of the negative energy solutions of quantum mechanics. So let's just go through some of the major successful predictions of quantum mechanics thus far. As we've seen, quantum mechanics predicts wave-particle duality not only of light but of particles like electrons, and this is seen in electron diffraction studies. Additionally, quantum mechanics predicts energy quantization and the atomic spectra from elements. Next up, quantum superposition. Experiments show quantum superposition, that is a prediction from quantum mechanics, is true. Next up is electron tunneling. We use electron tunneling in so many of our technologies to date. Quantum entanglement, something that I haven't yet spoken about, is also a major successful prediction of quantum mechanics. And finally, antiparticles. We found antiparticles, which are a direct prediction from quantum mechanics, being the negative energy solutions of the Dirac equation. So, one of the things in my title was quantum mechanics from the ignition of the sun. What did I mean by this? How can quantum mechanics ignite the sun? Well, it turns out that quantum tunneling is actually needed for the sun to generate its energy. We know that the sun primarily generates its energy through fusion, and specifically through the fusing of hydrogen into helium. During this process, two protons need to overcome the Coulombic repulsion between the two, and to do this, the energies are very, very high. Even though the temperatures and pressures in the sun, even at the center of the sun, while extremely high, they're not in general hot enough to facilitate this. So how does it happen? Well, quantum tunneling. Quantum tunneling allows some of these protons to overcome this barrier without having the energy required. This produces fusion and generates more energy, allowing for more protons to actually overcome this barrier. So yes, quantum tunneling is used in the sun in order to fuse its fuel. Another thing about quantum tunneling is radioactivity. I'm sure you've learnt about alpha decay, where an alpha particle is emitted from a nucleus. Well, how does this happen? Because if the alpha particle is inside the nucleus, surely it has to overcome the repulsive Coulombic force. Well, it does, but it has to do this via quantum tunneling. So yes, quantum tunneling is also used in radioactivity. So without even knowing it, you've studied quantum mechanics before. One last thing about quantum tunneling. We can use it in what's called electron microscopy. This is done via scanning tunneling electron microscopy. And this uses electron tunneling to image surfaces and even atomic planes. During this, an extremely sharp needle is placed very close to a surface sample and it's rastered over the sample. There's a potential difference between the surface and the needle, and electrons can tunnel through this potential surface from the surface to the needle, and we can record a current. The tunneling probability is very sensitive to changes in the width of this potential barrier. So, if there are places on the surface which are lower than other places, then this will be picked up by the current, and we can create pictures like the one shown on the slide. These are atomic planes of gold. So this is just another thing that we can use quantum tunneling for. There's another electron microscopy technique that I'd like to talk about that uses quantum mechanics, and this is scanning transmission electron microscopy in comparison to scanning tunneling electron microscopy. They are two different things. I did get confused because the two microscopy techniques are both referred to as STEM. So in scanning transmission electron microscopy, electrons are fired at a sample surface, and these electrons scatter from heavier atoms more than lighter atoms. And this scattering uses quantum mechanical principles. So, when these electrons scatter, we record the electrons that scatter at very high angles, and we use this to produce an image to show atomic columns. And this is on the absolute limits of science. So I just want to show you a few STEM images that I actually took during my master's research year. So two of these are mine, and one of them is from one of my supervisor's papers, but here they are. If you can see, these are individual atomic columns. We can image individual atoms with this technique. So not only is quantum mechanics, not only does it have consequences for some of the larger scale objects like the sun, but we can also use it to image atoms. This blew my mind when I was finally able to take some of these images. They are some of the coolest things, and they are on it. This is cutting edge research. This is on the edge, the frontier of science. Next up, electron microscopy actually helped us with the coronavirus. The image on the left was taken with a method called transmission electron microscopy, where instead of scanning a beam of electrons over your sample, you just fire a big parallel beam and you record the electrons on a plate. So on the left, this is coronavirus. This image was taken via transmission electron microscopy. TEM, as it's called, allowed us to visualize the actual morphology of the virus. It allowed us to study the viral envelope and the spiked proteins, and also observed how the virus got into cells. And a reconstruction of the coronavirus was then produced on the right-hand side, and I'm sure we've all seen this in the news when coronavirus was very big and we were in lockdown. electron microscopy is paramount to modern material science. And why do we care about this? Well, throughout history, entire ages have been named after materials, like the Stone Age, the Bronze Age, the Iron Age. And our future is in materials. If we want a greener world, then we're going to need to understand more about the functional properties of materials. And to do this, we need quantum mechanics. So, I just want to summarize everything that we've been through. This has been a whistle-stop tour of quantum physics and its development. We've seen things like wave-particle duality, the quantization of energy, the inherent uncertainty in systems. We've seen quantum tunneling and how it's used in the ignition of the sun, and also how quantum mechanics allows us to image atoms. So, I ask you, is there more? Absolutely, there is absolutely more. One of the coolest things that I studied during my time at university was a subject called quantum field theory, which just extends the idea of quantum mechanics, and it quantizes fields like the electric field and the magnetic field. This is used all over particle physics, and it's a very beautiful theory. So if you are interested in it, I would highly recommend you study quantum mechanics. It's one of my favorite topics in physics, and I could talk about it for as long as possible. But this is the end of my whistle-stop tour through quantum mechanics. So I hope you enjoyed, and thank you for listening.